So what we had was something like this. GS is equal to 5000 S plus 0.2 upon S into S plus 10 into S plus 50, from where we wrote G of j omega is equal to, we finally saw that it was 2 by j omega times sorry right. So first let me draw just the magnitude plot here, whatever space we have remaining here, right? Okay, so first let us mark out the corner frequencies. So somewhere here we will have 0.2, which is a critical point. Then we will have, of course, this as a critical point, and then we will have another critical point, right? So let us suppose this is 0 dB. Sorry. Yeah, so this is 0 dB. Zero. This is minus 20. This is minus 40. This is minus 60. Likewise, we have 20, 40, and 60. Again, the first thing that we have is, okay, I'll again color code this. Okay, fantastic. So let me use red for this, blue for this, green for this, and purple for this. So I'll draw them individually, and at the end we shall see again, just like the trick we used the other day, we'll not draw this separately because we know what, sorry, that's in the phase plot. So anyway, we'll not draw this two separately. So let me just simply mark it out with a black circle. So these are the different types of terms that we have. All right. Okay. Good. So now, when we want to draw the red one, so what happens for the red one? It comes all the way up to 0.2 and then takes off at, so this is 0.2, then this is somewhere here is 2.0, which is 1 decade above 0.2, so it should be at this. So this is corresponding to this term. For the blue one, similarly, now we will have starting off in the low frequency asymptote, and it will take off from 10, but in the other direction. So at 100 it will be, at 100 it will be here at minus 20 dB. So the blue one comes in like this. Again, this is a straight line. So the second one. All right. And finally, the green one. Okay, the green one starts to show its effect only at 50. So this is somewhere here will be, sorry, a bit here maybe. Let me just erase that. Oops, I have to draw that line again. Okay, so as I was saying, somewhere here will be 500, which is just 1 decade above. So this will be 2. Okay. All right. So this will be a parallel line. This green one comes all the way here up to this corner frequency and then goes off. So these are parallel lines, even if they don't look like it, but these are both at going down at minus 20 dB per decade. Okay. And finally we have the purple one. So what's the purple one going to be like? It's going to intersect at this point, isn't it? And 1 decade above, 1 decade below, which is here, it's going to be here. And over here, it's going to be here. So this is what we are essentially looking at. Okay. So now we have our asymptotic plot. So now what happens? Just take a quick look at this. So if we now want to take an amalgamation, so let me use some different color. What other color should I use? Okay, let me use this particular color for the combined plots. Okay, so up until this point, that is the corner frequency, we must follow the integrator. Yeah, sorry, we must follow. Oops. Okay, let me just get rid of that. Draw that purple line. Yeah. So that was the integrator. Yeah. So now we want to draw the combined effect, all of these, again using a different color, such as this. So you see that up until this point here, uh-oh, okay, we haven't really missed out on anything, except that we have deleted some of the writing there. So this was okay. This is 1.0. This is 0.10, and this is probably just a decade. Yeah, this is 1. Okay, fine, and we're good. So this is 0.20. Yeah, quite sure that's right. Okay, so I'll have to be a little careful while drawing this because somehow I'm touching this in the fashion that so as to move this plot. Okay, so here now we have up until this point, this is the combined plot because everyone else is contributing 0 dB from here. In this segment now, in this region, you see the combined plot remains flat like this, and hereafter this is the region. So this is the range of frequencies that we're talking about. In this, it remains flat because nothing else other than this red line and the integrator are active, and the sum of these two is a constant within this interval. Now what happens beyond this? It continues to remain a constant till at this point. Now it is called upon to go down further. Okay, so it starts to descend at 20 dB per decade until this point here, where it starts to descend even at a steeper rate of, so this is minus 20 dB per decade. This is also minus 20 dB per decade. And here onwards, it starts descending at twice the rate. I don't know, please don't take me or hold me to this, but that will go at 1000. I didn't do any calculations. So this is minus 40 dB per decade. So then the overall plot becomes this brown line, this chocolate brown line. This, and this. So you see there is a switching that occurs only at this point, at this point, at this point. So these, so there are these 3 points where, and these 3 are corresponding corner frequencies for the different terms. So the lesson to be taken home is, if you have an integrator, you will obviously be descending at a rate of minus 20 dB per decade for lower frequencies until you come across the first corner frequency where, because it's a 0 here in this particular example, the zero effect of the 0, which is to have a plus 20 dB per decade, cancels out this minus 20 dB per decade, and then you carry on with a 0 or slope of 0 flat line until you come across the next corner frequency, whereupon there is an additional effect of another pole, which is another minus 20 dB per decade. So 0 minus 20 dB per decade. So that's the slope that you hold on to till this point. Again, at this point, there is another pole which adds its effect of minus 20 dB per decade. Therefore, it becomes minus 40 dB per decade. So if I am to now draw it afresh, basically, this is the way I would do it without even thinking. So I know that there is a 0 at 1 plus j omega by 0.2 upon 1 plus j omega by 10 into 1 plus j omega by 50 by j omega. So if I want to plot this, remember there's still a factor of 2, which is what we addressed right at the end. So this is the 0 dB line. This is 0.01. So now I can do it once I've seen how the stuff works. I don't need to really draw these even separately. I can just, by visual inspection itself, tell how it would behave. That is the beauty of this method. Okay. So now I know that this 0 dB line is supposed to be crossed by this. So in one shot now, I will attempt to draw this whole plot. Okay, 20 dB, 40 dB, 60 dB. This is minus 20, minus 40, minus 60. Of course, I did not account for the corrections, which is what I had done the other day. And probably that might have confused some of you. So if you want to introduce corrections now, you will introduce a correction here, another correction here, and another correction here. Those are the corrections at the corner frequencies. But let's just leave it for now and just focus on the asymptotic plot. As I said, for these first order terms or these integrators, you don't really need to perform those corrections. It's only for the second order term where you have that resonant peak MR. Yeah, that's when the correction becomes more interesting and more significant too. Okay. All right. So then, now as we were saying, so here it's going to be the integrator here. So that's our integrators line. So let's just quickly draw the corner frequency. This is 0.2. This is 10. And this is 50. So we draw lines like these, vertical lines. These are the different critical corner frequencies at which some change happens. So until we approach this, we really need not worry. So first, because of the effect of the integrator, draw this. This is 0.2. So in one shot I will draw this. So till I approach the first corner frequency, I will keep going like this. I've approached the first corner frequency now, so, and which happens to be a 0. So the effect is to weaken the effect. So this is minus 20 dB per decade. That's because of the integrator. Then I encounter a 0 which nullifies this slope of minus 20, so it becomes a flat line. So it goes like this and goes till 10. Then at this point there is the effect of another additional pole. So it will start going down. Okay, again at this point it encounters another pole. So now this is minus 20 dB per decade, and from here onwards it goes down at minus 40 dB per decade. So this gives us, in one shot, without thinking of the individual components also, you can just mark out those corner frequencies and quickly draw the asymptotic magnitude plot for the composite transfer function. Okay, of course then you introduce the corrections. So that's about the magnitude plot. So what about the phase plot? So now we have space and we can show it more elaborately, unlike in the okay. Okay, one thing that I forgot to mention is now, once we've done that in this case, we have still not accounted for the k, the constant term, which is 20 log 2 is equal to 6 dB. So basically what that k will do is it will just lift every point on the plot up by 6 dB. Instead of that, we will say that we will call this 46, 26, 6, and similarly every one of these will raise by 6. So we'll call this minus 14, minus 34, minus 54. All right. Now this becomes accurate. So now you can consider this 2 also here. Okay. Or I could have just drawn 6 dBs above with some other color. I could have just drawn something like this. Yeah, it's the same thing. I chose not to. I chose to change the y-axis labels instead. Not the label, the y-axis values themselves, shifting them. It's not wrong. It's something that we can always do. Now we have phi of omega We start from the same sort of values that we had for the magnitude plot. 1.0, 10.0, again we mark out the corner frequencies and pick them up for special treatment. 0.2, okay, 10, okay, and maybe somewhere here we have 50. So these are corner frequencies. All right, at which we expect some jumps to happen. All right then. So what are the labels, what are the markings on the y-axis that we are now interested in? Okay, so let us just, let's say we take this to be 0, this to be 90, and this to be minus 90. So just like we took the effect of this constant term right at the end while drawing the magnitude plot, here while drawing the phase plot we will take the effect of the integrator last, because the integrator contributes a constant phase here. Yeah, excuse me. So because the integrator contributes a constant phase here, we will take its effect to appear last. So what is the first term whose effect we want to see? The effect of the first 0, because as we approach from the left, the first term we encountered is this 0 here. What would the behavior be like at the 0? We know that, again, this will vary from book to book. So some books will take it to, like if this is 0.04 and this is 1 and this is, let's say, 45 degrees, this is point, okay. So the first one is okay, that's the first one, the effect of 0 at point 2. The effect of the pole at 10 would be, let's say, so 10, this will be somewhere here, will be 10 by 5 is 2.0, not exactly here, maybe somewhere here, and this is 50. So you'll have this, sorry, this is a straight line even if it might look otherwise. Okay, as for this 50, that is 10. So let's consider the blue one. This is 10 and 55s are 250, which would be probably somewhere here. Okay, this is probably 250. So for 50, it's going to come from this. So we're going to consider the blue line. So it's going to be here and here. Sorry, and then we'll have to have this line. It's not going to really go down there, is it? It's not the magnitude plot, it's the phase plot. So I mistakenly drew it drooping from there. So, okay. Yeah. So that is the asymptotic phase plot. All right. So if we now want to draw the combined effect of this, what we shall be doing is, we want to draw the combined effect of this, what we shall be doing is as follows. Until this point, everyone is at 0. Yeah. Excuse me. Then, from this point on, it's only this fellow that has any effect. So that is it. Then you have this, but at this point it starts to reduce. Yeah, starts to reduce like this at the same rate as at which this rose. Yeah, and then from here it starts to reduce at twice the rate, so at a steeper rate. So what is the net effect of this? You see, the indication is that at this point this has become minus 90. So maybe somewhere here, yeah, okay. So at this point it starts to droop at a faster rate. But how far will this carry on? Okay, because you know that at this point, yeah, this fellow, sorry, not at this point exactly, wherever this, it's at 50, is it? Yeah, where does this hit 0? It hits 0 at 50. So yeah, at this point, the effect of this and this cancel each other out. So the value of the overall function is this. So you can draw the straight line through this point. Yeah. So it will pass through this. Is it not? Because this is at minus 90 and this is at plus 90. So they cancel each other out. So the only value remaining is this. All right. So then here, and right down to this point, if you carry on like this, at this point, yeah, at this point what will happen is this green and the red continue to cancel each other out. Okay, sorry. So yeah, so this is a corner frequency. All right, so things should sort of change here. So basically all that you'll be left with, because this green and the red ones are cancelling now each other out, so all you'll be left with is essentially this, if following this blue line, this, you'll cling on to this, you follow. So from here it's everyone is 0. Between this 0.04 to 1, you'll only be following the red one because everyone else is 0 here. Okay, between this and this, again the same thing, you'll be following this red one only. Between 2 and I'm sorry, between 2 and 10, no other change happens. So this comes down at the same rate as this slope. Okay, so this is like, it's a subtraction of this. Okay, but here at this point now, there's a further addition to the slope, which results in a fact that at this point, which also happens to be 5 times 10 and also a corner frequency, so therefore this and this coincide. So therefore at this point the red one and the green one are balanced by each other. So therefore in the phase contribution the only thing that is left is the blue one. So you'll latch on to this blue one, and hereafter at every point the red and the green will cancel each other. So the overall asymptotic plot is then this, 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 and this. Okay. But now we are not done yet. What still remains, what still remains for us to accomplish here is the fact that we haven't accounted for this integrator's effect. So what will the integrator do? It will just push it down by a further 90 degrees. So again, we will adopt the same trick, not really a trick. So I'll just call this, let's say, minus 180 degrees. I'll just call this minus 90 degrees, and I'll just call this one as the 0 degrees. Yeah, and we are done. So this is the phase plot. So I just wanted to clarify. Now if you want to do this in one shot, just like we did for the magnitude plot, you can still do it quickly without giving it much thought. Of course, the points you have to mark out are 0.01, 0.1, 1.0, 100.0, 0. So the points you have to mark out are 0.2, 10.0, 50.0, sorry, 50.0. all right, you have 0 here, minus 90 here, and plus 90 here. So again, because we've drawn this, we should also draw those 1/5 and 5 times. So this is also a crucial point for this. So 1/5 and 5 times, so that is going to be 2, and 50 is already there, and 50 is 1/5 is 10, and 5 times is somewhere here, 250. All right. So if you now instead don't want to draw those, remember initially we had said that those high asymptote and the low asymptotes, they actually meet at, they don't meet here in this case of the phase plot. That was a problem. Unlike in the magnitude plot, the phase plot has the high frequency asymptote and the low frequency asymptote exhibiting a jump discontinuity at the corner frequency. Okay. So what happens? So first up, you just proceed like this to draw up till here. Then you have a jump discontinuity here. So go up to the next one, which is 10 in this case. So go up to 10 here. Yeah, so this takes care of the first term. Now at 10 what happens? Because there's a, yeah, so again you're back to this. So these are without accounting for the corrections. All right, without accounting for the corrections, we're just drawing the asymptotes. Okay, so you come down by 90 degrees and you come a further 90 degrees down here from this point on. Okay. Okay. So essentially what we have is something that looks like this. Yeah, something that looks like this. Okay. Yeah, I think that's about it. So this is how it looks. Now if you want to incorporate the corrections, you know that 1/5 of the way down is here and halfway down is I'm sorry. So you want to join basically 1/5 to halfway down, which is basically these points. You want to incorporate this correction here, and then you want to take down this 10, whose point would be here somewhere 2, and at 10 it will be equal to 45 degrees, and then this will come down at 50, and for the line at 50 here you will have 50 by 10, so this, and at 50 it will be like this, and you have 250. So you have these lines. These are your corrections to the asymptotes, because here there is a jump discontinuity. To smoothen them out, this is what you do. Okay, so these are the individual corrections now. All right, so now this is the asymptotic plot. If you want to do a better sketch, just take upon yourself this. Something like this. If you wanted to incorporate this correction, so this brown one. So in one shot, you see, without drawing those individual components, just by marking out these corner frequencies and some of those asymptotes, we've been able to draw the overall phase plot with respect to omega. So this is what you will be expected to draw. Once you've practiced a few problems, you'll be able to see how this happens. Okay, so I just wanted to clarify that. So now, as promised, we shall look at something called non-minimum phase system. Non-minimum phase system. Now suppose you have a transfer function given by s minus 1 upon s plus 1 into s plus 2, and okay, s minus 4, let's say, and this is s plus 4 into s plus 1 into s plus 2. Now with our newly gained insight, we don't need to draw those individual components, but let's say we are drawing this 20 log m dB. What does this imply? So this is a 0 dB line, this is minus 20, this is minus 40, and this is 20, and sorry, this is 20 and this is 40. All right. This is 0 0.01, 0 0.1, 1.0, 10.0, 100.0. We don't need to go to 100 though in this case. Anyway, the point is you mark out the corner frequencies. The corner frequencies would be 1, 2, and 4. So if you take both of these, this is G1 of S and this is G2 of S, and if you just write it down as such, maybe I'll just adjust the gain so that magnitude is taken care of. Yeah, it's just a factor. It's just going to move up or down, move the entire plot up or down. So I'll just adjust it to be 0.5. The point is that the magnitude plots of both these transfer functions G1 and GS would look identical, right? And what would it look like? So between this and this, I would follow the minus 20 dB per decade. This is 2 and this is 4. So again here I would follow minus 40 dB per decade here. So that's the effect of 2. So this is minus 20 dB per minus 20 dB per decade. This has a slope of minus 40 dB per decade until it approaches the next corner frequency, which is a 0. So it will again start to go at minus 20 dB per decade. So this is what the magnitude plot of both these functions are going to look like. So remember the question we posed the other day? How to identify the system. So now if you are given just the magnitude plot, clearly you can see that it's impossible to distinguish between these two transfer functions. So the only way to see that there will be a difference in these two transfer functions is when we plot the phases of both of these. Yeah, because clearly the magnitude function will not let us uniquely determine. So what is so special about the particular transfer function G2 in this case, which has all its zeros on the left half plane? Yeah, as compared to this. So this is basically the one that we call as minimum phase. So let me write that down formally. If all poles and zeros of the transfer function are in LHP, we call the system a minimum phase system. Okay, if at least one zero lies in the RHP, it is called a non-minimum phase system. So what is minimum about the phase, or what is this minimum, this notion of minimum? So far we haven't been equipped to answer this question because we didn't understand frequency domain plots. Yeah. Now that we know what this is, we find ourselves capable of addressing this question here. Okay. So for example, let us consider 10 s plus 1 over s plus 10 and 10 s minus 1 over s plus 10. So by our definition, this qualifies as minimum phase and this qualifies as non-minimum phase. So this is G1, this is G2. So what is it in the phase plot that makes one of them a minimum phase one and the other one a non-minimum phase one? Excuse me. All right. So let's say we have this. So this is 0 degrees. This is 90 degrees. This is 180 degrees. Yeah. So consider the minimum phase system. What is the phase contribution? What is the phase contribution at very low frequencies? So for instance, let us start with 0.01, 0.1, 1.0, 10.0, 100.0. Okay. So this is the conventional one, and we know how to plot its how how to plot its phase function, isn't it? So of course the standard way to go about this is 1 and 10. So we mark out this 1 and 10. Yeah. So we say that up until this point we follow this, then we follow the higher asymptote for this, but then again the 10 brings it down, so again the lower asymptote. So it's something like this, a gross approximation. But now, however, so I'm not drawing those things again. However, if I want to draw a better plot than this asymptotic approximation, it will be something like this. Okay. On the other hand, if you draw for the non-minimum phase system, yeah, what happens? Just look. As omega is very small, this will not contribute much. But what about this, the numerator? It will contribute 180 degrees. So it starts basically from here. Yeah. So if I want to draw this for the second one, I would draw here 180 degrees. And then, unlike what is usual for a zero, here the zero's phase will behave like the phase plot of a pole, which is to say that normally look at this frequency, corner frequency of 1, it had raised the, or given a lead. By the way, incidentally, this is also the origin behind this description of a lead or a lag compensator. Yeah, because of the phase plot. So you see now when you place the zero to be closer than the pole, which is the usual definition of a lead compensator, you get a phase plot which provides a lead within a certain frequency band. So this is also a lead compensator. Of course, we're not talking about this. We're talking about the minimum phase one. So this is the lead compensator. By the same token, if you reverse the pole and the zero and take the zero to be at 10 and the pole to be at 1, then you will see that you will have a lag compensator. So you'll have a phase lag within this particular frequency band. So this is also something that is used to design lead and lag compensators in the frequency domain. So you are specified that within this frequency band, I need a phase lead of so and so, and within this frequency band, I need a phase lag of so and so, and accordingly you design. So here the specifications will be in terms of those frequency domain performance metrics. Anyway, we digress a bit, but I thought this is important and interesting. So now you would also know that why that sort of a transfer function is called a lead compensator. Anyway, from the frequency domain also, this is the explanation. Okay, so coming back to this, look here, what continues to happen is that now this behaves as the asymptote, because now it's s minus 1 beyond the corner frequency. Okay, so for s greater than 1, now the real part continues to remain negative. Yeah, it's only the imaginary part that grows. Okay, so you will still be living in this domain if you move. So do you see that? So you will not be achieving a phase lead of 90 degrees over and above 180 to move to 270. Rather, you will be moving back to 90 degrees only. Yeah, because remember, this is the term that's responsible for this is tan inverse of omega by minus 1. Yeah, that is what the phase contribution of this term is. So since that is the case, yeah, it doesn't matter what you do. At this point, it will be beyond you. So this is going to be 135 degrees. Because the cos is negative and the sine is positive. So this is 135 degrees here. Out here somewhere. Yeah. This is 35 degrees. Of course, here we are not really interested in that. So therefore, it will start to descend like this. Furthermore, beyond this point, it will follow this asymptote. So what you're basically looking at is a plot, something like starting from here, passing through here. Oh. Okay. Starting from here, somewhere like this, something like this. So now you'll realize why this is called minimum phase and the second one is called a non-minimum phase. Look at the net change in the phase in going from low values to high values. It is 180 degrees. Okay, or if you like, minus 180 degrees is the total change. Whereas if you look at this, the minimum phase one with all its poles and zeros on the right, the net change is 0 degrees. So because the minimum phase plant among all transfer functions that have identical magnitude plots, so here's the explanation, let me write it down. Among all transfer functions having identical m omega, or rather 20 log of m omega plots, the net change of phase in going from omega tends to 0 to omega tends to infinity is minimum for the minimum phase system. Anytime you have at least one of the zeros on the right half plane, it ceases to be a minimum phase system because it contributes more. Let's see how that is true. So what is the total contribution? Let's say you have a transfer function gs. We'll take the simple first order factors. This is the same for the second order factors, right? So let's say this is s plus zi, I is equal to 1 to m, and this is pi, I is equal to 1 to n, s plus pi. Okay, so the net change in phase, suppose zi, pi are all positive, right? So the net change in phase delta theta from 0 to infinity is equal to n minus m into 90 degrees. We're already familiar with this sort of writing, isn't it? Of course, you can write this with a minus sign also. Yeah, so usually n is greater than m. So the net change is this. Now suppose r of the zi's, so this was this. So suppose all r of the zi's are in RHP while all n pi's are in LHP. What happens then? Then this delta theta from 0 to infinity becomes minus of. So what happens to the overall contribution? So remember that these R fellows, these will now team up with the poles. So they get added to the poles and these will take the effect away from the zeros. Times 90 degrees, which is equal to minus of n minus m plus 2r 90 degrees. Yeah. So what happens then? If this is a phase contribution, you take the absolute magnitude of this. Yeah. Suppose n is equal to 20. Suppose n is equal to 20, m is equal to 10, r is equal to 4. So what is this? Then this turns out to be minus 900 degrees. Whereas this turns out to be 10 plus 2r, which is r is 4, right? Yeah, 4 2s are 8. This is 18 into 90 degrees, is it not? So how much is that? 18 9s are 162. 1620 degrees. So that is going to be the net phase change in going from 0 to infinity. So anytime you have r of those in the RHP, you see you can never match up to this. This is the minimum amount of phase contribution you can have from a particular transfer function having n poles and m zeros. When all your poles and zeros are in the LHP. The moment at least one of them comes out to the RHP, the net phase contribution will be n minus m plus 2r. And this is going to be a greater phase change than this. So therefore, these having zeros in the right half plane are non-minimum phase systems, and this is a minimum phase system. So I hope that that term is at least clear to you. So we have explained what lead and lag indicate in the context of these magnitude plots. We've also shown you what minimum phase and non-minimum phase imply in this case. We've also in the preceding segment of this lecture seen what the resonant peak, MR is. Yeah, this is particularly significant for the second order responses. Okay. So now I want you to think about this. Remember, when we spoke about in the root locus case, when we spoke about choosing the constant gain of the system, yeah, why did we want high values of gain? Suppose you have a Bode plot that looks, I'm not just drawing this thing here, I'm just doing a rough sketch here. Suppose this is something like this, and then again something like this. So this tells you there's a pole here, there's a second pole here, and there's a 0 here. This is 20 minus 20 dB per decade. This segment is minus 40 dB per decade. And this segment is again minus 20 dB per decade. Let's say these are just certain corner frequencies. We really aren't concerned about the numerical values of this. Now if you increase the gain of this, let's say this is the 0 dB line. Okay. If you increase the gain of this fellow, so what happens then? If you increase the gain of this fellow, it just has the effect of pushing it up. The entire frequency response, the magnitude part, will be pushed up. The phase part will not be affected at all, is it not? Yeah. So let's say we have the phase here. Okay. So why did we want higher gains in the first place? If you remember, higher values of K implied that the steady state errors will be low. So in general, we want to minimize the steady state errors. There's also another motivation behind that. Okay. So now we will explain the concept of what is called a bandwidth. This is again something that you've heard pretty often when you're dealing with systems. So we say the system's bandwidth is given by that frequency at which it has an attenuation of 3 dB. Okay, so maybe this, for this particular system here, we will call this the omega bandwidth. So the point is that it is always desirable to have higher bandwidth. So apart from the motivation that comes from the time domain, which is to minimize the steady state error, that tells you that you should have higher values of gain, that dictates that you have higher values of gain k, it is also the desire to improve or increase bandwidth that should also push you towards having higher values. Why? Because the moment you push this entire plot up, you see the point at which this intersects with the constant 3 dB, minus 3 dB line moves to the right. So if I now draw, let's say, okay, let me take the red one. So if I just draw a lifted version of this, yeah? If I draw a lifted version of this, so now this becomes my new bandwidth. So desire for higher bandwidth leads to seeking higher values of k. Now you might wonder, in terms of the time domain specifications or performances, what does this high value of bandwidth have to do? So in order to answer that, let me just quickly draw this. Okay. Let me just quickly draw this here. I mean, why would we want this at all? Think of this typical second order response that we had constructed earlier. Yeah, something like this. This is minus 40 dB per decade, and this is maybe the 0, and this is the MR, 20 log MR. Okay. If you see this, of course, I have expanded this significantly, but now if you want to find out somewhere over here, so maybe this is where, probably this is omega n for the second order response. Yeah, so this is basically, we're trying to draw j omega by omega n whole square plus 2 zeta j omega over omega n plus 1. Yeah. This is what to the power minus 1. This is what gj omega is in this case. Okay. This is what we're trying to draw here. So this is the magnitude, right? So anyway, so the point is, if you increase bandwidth, it basically implies that omega n is larger. But what does that essentially tell you? So the bandwidth is proportional to omega n. Yeah. And what else do we know? If you recall, when we drew those on the complex plane, this is the imaginary, this is the real part. So the constant omega n loci, which is a circle, this is the constant omega n loci. Remember, that corresponded to approximately the constant rise time loci too. So basically, if you want to have smaller values of rise time, then you want to have higher values of omega n, and omega n is proportional to bandwidth. Yeah. So it makes sense then that if you want smaller rise time, that is, this is also a measure of speed of response, mind you. Earlier, when we were dealing with time domain compensator design, we only focused on the settling time as a measure of the speed of response, and settling time gives you how quickly the response damps out. But remember, rise time is also an indicator of the speed of response, how quickly it responds to the initial application of the input, right? So how soon it rises, how soon it attains the peak. So the peak time and rise time are both related in that way, in the similar fashion. So the how quickly the transients decay is being defined by the value of, is being described by the value of the settling time. But how quickly the system responds in the first place depends on the rise time. So if you want the system to respond very quickly, maybe it has higher oscillations thereafter, so the settling time may be high, but at least if the rise time is low, it means that as soon as you apply an input, the system immediately begins to respond to it. If you have larger values of rise time, it means, and lower values of settling time, it means there will be lesser oscillations. But in order to attain the first peak itself, it will take significantly long amount of time. Yeah, significantly large amount of time. So therefore, if you want to specify your speed of response in terms of rise time, it makes sense to have a larger bandwidth. And the way to have a larger bandwidth, as we've seen, is by pushing this upwards. The way to shift it upwards is to increase the value of the steady gain, this DC gain K. All right. So here, of course, you have to pull it out. This is one unity. So that is why we want larger values of K. But remember, some price has to be paid in terms of stability. So there will be more oscillatory, especially when we have third order system. So let me take this example now. Let me take this example now. I'm sorry. So let me take 1 by s plus 1 into s plus 10 into s plus 50 over 500, just to adjust. Yeah. This is what I'm going to choose. So let's say this is 0.01, 0.1, 1.0, 10.0, 100.0. Okay. So this is probably going to be 0 degrees, minus 90 degrees, minus 180 degrees, and minus 270 degrees. Okay. So we quickly drop on the 0 dB line here. So excuse me. So of course we go all the way up to 1 without much of a care in the world, and then we have 10. So then we have 10, and then somewhere here we have 50. So at 1 it starts descending like this, then at 10 it goes up like this. So let me make this 5000 then. Okay. And then at 10 it starts sorry. So this is how it goes down. This is minus 20 dB per decade. Then it starts descending at a faster rate of, this is minus, okay, so let's say this is a 20 dB line, because now we have amplified the gain by 10 times. This is minus 40 dB per decade, and from 50 onwards it goes at an even faster rate, which is, so these are the corner frequencies. This is minus 60 dB per decade. So remember that the root locus of this system, I'll draw it roughly here. You had minus 1, minus 10, and minus 50 here. Yeah. So if you remember the root locus, it will exist somewhere here, and then it will break away something like this and here. So over here is the critical value of gain K. So even if you want very high values of K, and you can see that as you increase the value of K, in this case you might get further and further away from the origin, which means that your omega n value is increasing. Yeah. And if your omega n value increases, okay, it essentially means that you have a larger bandwidth. Okay, fine. So somewhere here, now recall, if this is your 0 dB line, if you now further increase this, so let's say there is a k here, this is for k is equal to 1 and k is equal to 10. Okay, so this black line corresponds to k is equal to 1. So this is where you cross the 0 dB, the constant 0 dB line, and this is what we call the gain crossover frequency, GCF, the gain crossover frequency. How is this relevant? You know that in order for a point to be a root, you need 1 plus g is equal to 0. Yeah, so in order for an imaginary number to be a root, you want that 1 plus g of j omega is equal to 0 for some real value of omega. So suppose now there exists some such omega, then what would happen at that particular value of omega? Let's say somewhere here, we don't know what it is. Not only is it important that you have the gain equal to 0 dB, which is implying unity, but also you need the phase to be minus 180 degrees. Okay. All right. Now suppose you take the response of this one. Okay. So what is the phase plot going to look like? A quick scanning will reveal to us what the phase plot will look like. So this, then there is a step jump here, and it goes on till 10 here. Then there is a step jump here, and it goes on till 50 here, and then there is a step jump here, and it goes like this. Yeah, so you'll probably have an actual phase plot that looks somewhat like this. Yeah, something like this, then like this. Sorry, let me redraw that previous line. Yeah. So at low frequencies it touches the asymptote, comes close to the asymptote, then something like this, then something like this, and then something like this. This is what the phase plot is going to look like. At some value here is going to cross the minus 180 degrees, and this is what we call the phase crossover frequency. The phase crossover frequency. Now you will be in trouble if corresponding to some imaginary value, yeah, so that is a real value of omega, you have the phase crossover frequency and the gain crossover frequency coinciding. All right, do you follow? So this is the phase crossover frequency, this is the gain crossover frequency. So typically, let me just write that down. For an open loop stable system, omega PCF, so phase crossover frequency is greater than omega GCF. Suppose this is the case. Okay, so that means that you can still keep increasing your gain, because if you increase the gain now further, you're basically lifting this magnitude plot up and you're shifting the gain crossover frequency to the right. What happens is, then you can see this from the Bode plot now, an increase in K leads to omega GCF moving further to the right and coming closer to omega PCF. So at the value of k for which omega PCF is equal to omega GCF, we have arrived at k is equal to k critical. So this is the upper value of k. Okay, so we call this the gain margin. Yeah, so if you can keep increasing your k up to by a certain factor, so let's say you start with k is equal to k0, and then you have this tuner, so k is equal to gamma times k0. So you start with gamma is equal to 1, and clearly if it's open loop stable system and omega PCF is greater than omega GCF, then for gamma is equal to 1 you still are pretty much safe. This will be clearer when you do Nyquist criteria, by the way. So then you'll be able to see the clearer picture, the unified picture. But for now, at least you can see that the omega PCF lies to the right of omega GCF. It means that you can still keep raising this gain k, which is what the root locus also suggests here. Yeah. So that means if this is an open loop stable system, you initially start for k is equal to 0, low values of k, you initially have your closed loop poles in the left half plane only. As you keep increasing k, you start moving closer and closer to the right half, to the imaginary axis, until you migrate to the right half. That is the same thing that is being revealed by this Bode plot here. If you increase k, you are lifting this magnitude plot without affecting the phase plot, thereby pushing the gain crossover frequency to the right, and it comes closer to the phase crossover frequency. All right, if it comes closer to the phase crossover frequency at the value of k, so at some gamma crit k0, we have omega GCF is equal to omega PCF. Then gamma crit is the gain margin. Okay, so this is how you define the gain margin of a system. This is a very much a frequency domain term that you're likely to encounter, but you can now unify the picture and clearly see how this relates to the root locus as well. Basically, you start with some nominal value of k, and by what factor can you keep increasing it? So if you have a positive gain margin, it means that you can keep increasing your gain. If you have a negative gain margin, which is to say that suppose omega GCF, suppose omega GCF is greater than omega PCF. What does it mean? What does it mean? What it means is that, now look, it means is that this GCF is to the right of PCF. So in order to be on the safer side, you have to reduce the gain. So you have to reduce the gain to get to the imaginary axis. So if it's open loop stable such as this, if it's open loop stable, if the system is open loop stable such as this, and you have to reduce the gain to go to stable position, it means that your gain is already too high to start with. Okay, so in that case, you'll have and G is open loop stable, then the nominal gain is already too high and we need to attenuate, which is to say that you need to bring it, Anyway, we'll not be visiting this. So we need to bring it down like this. So every part then you bring down like this and shift the gain crossover to the left. Yeah, because you're already way off the mark. Attenuate, or that is choose gamma less than unity. So then in the log scale, if you write 20 log gamma is the gain margin in decibels. So if gain margin in decibels is positive, implies we can keep increasing gain further and still have stable closed loop behavior. On the other hand, if GM in dB is negative, we need to reduce gamma. Okay. So therefore, of course, all this is under the assumption that the open loop system is stable to start with. Okay. All right. So now we have explained gain margin. Additionally, there is also something called a phase margin. What is that? So these are actually indicators of robustness in some way. So if you have a nominal system, and it's not necessary that you are designing that gain explicitly. Over time, let's say the system, the parameters of the system, the components of the system change. So then the system's poles and zeros might shift, the system's gain might alter. So to what extent can you tolerate this change in gain K before the system becomes unstable? So that is the gain margin. By the same token, see, if you play around with these poles and zeros, or rather maybe not you are playing around with it, but because over time the system suffers the ravages of time and then these poles and zeros shift. So then maybe, just maybe, that this phase crossover, this phase crossover frequency also shifts more to the right by some manner. We don't know exactly what sort of changes in poles and zeros will lead to that, but suppose the phase crossover also moves around. Now if the phase crossover moves further to the right, so if the phase crossover moves further to the right, it is to our benefit. But what if by some manner, if the poles and zeros of the system change in such a way that the phase crossover moves to the left, that is detrimental to stability. So this phase margin and gain margin are basically together indicators of stability of the system. Robustness of the system. Robust stability of the system in some sense. So what happens is, phase margin, we've seen that gain margin is evaluated by taking 20 log g j omega, the magnitude that is, which is m omega, at omega is equal to omega PCF, which is to say that if you take this phase crossover frequency here, if you take this phase crossover frequency here and extrapolate this maybe somewhere here, then this is the amount by which you can still raise this, is it not? This is your gain margin. So the gain margin is evaluated at the phase crossover frequency. So at the phase crossover frequency, this is the amount of gain that you can still add, so that this point lies exactly on the 0 dB line. Okay, oh, this is the 0 dB, is it? Okay, then make it this. This is the 0 dB line. Okay, so this is the amount of gain margin that you have for the system, a positive gain margin. So you can keep raising this to this extent, because at all other points we don't care. It's only when for a magnitude, for a phase of 180 degrees or minus 180 degrees, the magnitude becomes unity, that we have imaginary roots which signify these poles, okay, from the root locus. So therefore this is the gain margin. The gain margin is evaluated at the phase crossover frequency, at the phase crossover frequency. By the same token, this phase margin is evaluated by how far you are from minus 180 degrees minus phi at, I'm sorry, minus phi, okay, let me just get rid of that. So the phase margin is given by minus how far you are from the minus 180 degree line minus phi of omega. Omega is equal to omega GCF. What does that mean? It means that the gain crossover frequency, which is when this crossed the 0 dB line, how much more phase lag you could have added. So you know that it eventually crosses the 180 degree line somewhere here. So this is the amount of phase margin that you have if this is the gain crossover frequency. I don't now really remember, so probably this is the gain crossover frequency. So remember, the phase margin is evaluated at the gain crossover frequency, and the gain margin is evaluated at the phase crossover frequency. Okay, these terms will be clearer again. I repeat, when you do the Nyquist criteria, you'll be able to visualize. You'll have a different flavor of these terms. But from the Bode also you can see. So clearly you can unify the concepts that we have acquired from the Nyquist criteria as well. Yeah. So we now see that from the Nyquist criteria, or I mean from the Bode plot also, we infer that for larger bandwidth or for smaller steady state errors, larger gains are desirable. However, if you keep pushing your gain to be larger and larger, there is this risk that you run, which is also the case in case of the, which is also something that we've seen from the root locus analysis, that if you keep increasing the k to larger and larger values, at some point it will lose stability, which in the Bode plot context implies that the phase crossover frequency and the gain crossover frequency overlap, and thereby giving you zero phase and gain margin both. Yeah. Okay. In fact, if you define it this way, then a negative phase margin is something that seems desirable. But this is really a matter of taste, and you can also define this to be phi of omega plus 180 degrees. In this case, positive phase margin is desirable. In this case, negative gain margin, phase margin. It's just a matter of defining. You just have to remember how you're defining it, is desirable. So more conventional approach is this. So this is phi omega minus of minus 180 degrees. So how far you are from the 180 degree line, that is the difference. So you can still withstand a lag of that much amount before your system gets unstable. So before we conclude this discussion on Bode plots, one of the things that I would like to particularly highlight is there can be another type of term which we haven't discussed. Most of the standard books also do not discuss this. So you can also have a pure time delay. apart from those first order building blocks, the second order building blocks, yeah, in the poles and the zeros, in the numerator and the denominator, you can have term like this also. So what would be the phase and magnitude plot for such a term like this? Clearly, if you replace this with e to the power minus j omega t, yeah, this is just cos omega t plus j sine omega t. So the magnitude is going to be 0 dB only. It's not going to budge an inch. It's not going to contribute anything. So this is a pure delay. So you can have a transfer function, let's say e to the power minus st over 1 plus s tau 1 into 1 plus s tau 2. So remember, the root locus tells you, and this is very interesting, the root locus tells you that you have two poles like this, and if you don't have the time delay, you'll see that the asymptotes go like this. So theoretically you have infinite gain margin. Yeah. So because the crossover never happens, and because at omega tending to infinity, you have the phase equal to 180 degrees, minus 180 degrees. Yeah, so the crossover never happens. And that is also revealed from this root locus, where you see that the asymptotes never go to the right hand side. But now, if you introduce this term, you cannot be sure anymore. And this is where we haven't seen how to deal with this sort of a term using root locus. Okay, because root locus cannot handle such terms which are not rational functions. Okay, this is an exponential. But here, the Bode plot is powerful, because no matter what this is, if we can get a handle over this, so this will allow us to draw the Bode plot. And phi of omega is nothing but minus, okay, so we just missed something. There will be a minus sign here. So this is minus omega t. Yeah. So what will it look like? This is omega, and again this is omega. So on a linear scale, this would have been a straight line. Yeah. But now that this is a log scale, remember that this is probably 0.1, this is 1.0, this is 10. So the nature of this is, let's say 0 degrees. Let's say from point 1 it's going to be just maybe something like this. So the phase plot is going to continuously decrease. So it's curving out because the x-axis is now a log scale. So the change in phase from 0 to from 0.01 to 0.1 is comparatively much smaller than the change from 0.1 to 1. Because remember, it's going at a straight line, linear rate in the linear scale. But in the log scale, this will go down very fast. So what does this essentially introduce? Now suppose you have the original transfer function, something like this. So this is the pure delay. And the original transfer function was, let's say, something like this, and something like this, and something like this. Okay. So this is, let's say, 1 by tau 1, and this is 1 by tau 2. Okay. So its phase plot would look something like, let's say this is 0 degrees. So this is, let's say, minus 90 degrees, let's say, just without loss of generality. And this is minus 180 degrees. Okay. So you go here and you go here. And the original phase plot would look something like this. So you would feel safe. If you did not know that there was this delay here, you would feel safe. Is it not? Because you know that the phase crossover, where you measure the gain margin, happens at infinity. And at infinity, this fellow keeps decreasing. So it goes to minus infinity. So therefore, there is an infinite gain margin, and you feel I can keep increasing the value of gain k without loss of stability. But remember, now you have this exponential term which is lying hidden here, and this is so latently dangerous because you are thinking that you are safe because you think that this is what your phase plot is like. But in a sense, this exponential term, which is a pure time delay, is actually adding this phase also. So at some finite value of omega, you will definitely go below. In fact, you will go at a quicker rate. So somewhere here you have already crossed. So this is your phase crossover frequency. Yeah. So if this is your phase crossover frequency, then you have only this much gain margin. So this is your amount of gain margin. Okay. This is the amount by which you can increase your gain. But if you are unaware of the existence of this delay, yeah, that is going to be very dangerous. If you're unaware of the existence of this delay, you might think that I'll keep increasing the gain k because I have only 2 poles. It's a second order system. How bad can it get? After all, I'll keep increasing k. The only thing that will happen is that these poles will go from the root locus. Also, you can analyze that these poles will go along the with constant real parts beyond a certain point. Unfortunately, that's not going to be the case because you've overlooked the effect of this delay, which does not have any effect on the magnitude but affects the phase. So adds a constant lag of minus omega, not a constant lag, as a linear lag of minus omega t. So therefore you have a finite phase crossover frequency rather than the infinite one that you had conjectured. And so in reality, this is this amount of gain margin that you actually have rather than infinite gain margin. So you have to be very, very careful about dealing with time delay systems. So this is what I really wanted to discuss and show. So now, given that we have discussed all of this, you should be able to handle all sorts of linear time invariant systems, even if they have time delay terms. So you might not find such examples in Norman Nice, but at least I hope that you've got the hang of this time delay, how to deal with this and cover for this in a Bode plot. Okay, you have to, the phase plot, the gain plot will not be affected at all. It's just the phase plot which will keep adding a constant value, a constant slope. Not a constant slope on the log scale though, a constant linear slope. Okay. Okay. So thank you very much. With that, we conclude our discussions on frequency response, at least the part that deals with Bode plots. Okay.